10 years after its discovery, scientists are probing the Higgs boson particle. On July 4, 2012, scientists at the laboratory CERN near Geneva announced the discovery of the Higgs boson, the long-sought subatomic particle that reveals the origins of mass. Scientists predicted the existence of the Higgs boson back in 1964 as a hallmark of the process that gives elementary particles mass. But finding the particle had to wait for CERN's Large Hadron Collider, or LHC, and in 2010, the LHC began smashing protons together at extremely high energies, while two large experiments, ATLAS and CMS, used massive detectors to look through the debris. The particle's discovery filled in the missing keystone of the standard model of particle physics. Those particles and interactions are behind just about everything we know. The particles serve as building blocks of atoms and transmit crucial forces of nature, such as electromagnetism. And the mass of those particles is key to their behavior. If electrons were massless, for example, atoms wouldn't form. Without the Higgs boson, then, one of scientists' most successful theories would collapse. The Higgs boson discovery dominated headlines around the globe. About 500,000 people tuned in to watch the live-streamed announcement, and footage from the event appeared on more than 5,000 news programs. Little more than a year later, the discovery garnered a Nobel Prize for two of the scientists who developed the theory behind the Higgs boson, Francois Englert and Peter Higgs, for whom the particle is named. Now, as the discovery turns 10 years old, that initial excitement persists for numerous particle physicists. Physicists have been working through a checklist of things they want to know about the Higgs boson. They spent the last decade cataloging its properties, including how it interacts with several other particles. Though measurements have so far been in line with the predictions made by the standard model, if a contrast turns up in the future, it may mean there are unknown particles yet to be discovered. The Higgs boson has a mass of 125 billion electron volts, meaning it is 130 times more massive than a proton, according to CERN. It is also chargeless with zero spin, a quantum mechanical equivalent to angular momentum. The Higgs boson is the only elementary particle with no spin. Because quantum field theory describes the microscopic world and the quantum fields that fill the universe with wave mechanics, a boson can also be described as a wave in a field. So a photon is a particle and a wave that arises from an excited electromagnetic field, and the Higgs boson is the particle, or quantized manifestation, that arises from the Higgs field when excited. That field generates mass via its interaction with other particles, and the mechanism carried by the Higgs boson, called the Brute-Englert-Higgs mechanism. The Higgs boson, nicknamed the God particle, was solidified upon its discovery, namely as a result of the popular media. Still, it's hard to overestimate the importance of the Higgs boson and the Higgs field in general, as without this aspect of nature, no particles would have mass. That means no stars, no planets, and no us, something which may help warrant its hyperbolic nickname. In 1964, researchers had begun to use quantum field theory to study the weak nuclear force, which determines the atomic decay of elements by transforming protons to neutrons, and its force carriers, the W and Z bosons. The weak force carrier should be massless, and if they weren't, this risked breaking a principle of nature called symmetry, which, just like the symmetry of a shape ensures it looks the same if it is turned or flipped, ensures the laws of nature are the same however they are viewed. Putting mass arbitrarily onto particles also caused certain predictions to trend towards infinity. Yet, researchers knew that because the weak force is so strong over short-distance interactions, much more powerful than gravity, but very weak over longer interactions, its bosons must have mass. The solution proposed by Peter Higgs, Francois Englert, and Robert Brout in 1964 was a new field and a way to trick nature into breaking symmetry spontaneously. An article from CERN compares this to a pencil standing on its tip, a symmetrical system, suddenly tipping to point in a preferred direction, destroying its symmetry. Higgs and his fellow physicists proposed that when the universe was born, it was filled with the Higgs field in a symmetrical but unstable state, like the precariously balanced pencil. The field quickly, in just fractions of a second, finds a stable configuration, but this in the process breaks its symmetry. This gives rise to the Brout-Englert-Higgs mechanism, which grants mass to the W and Z bosons. What was later discovered about the Higgs field was that it would not only give mass to the W and Z bosons, but that it would grant mass to any other fundamental particles. Without the Higgs field and the Brout-Englert-Higgs mechanism, all fundamental particles would race around the universe at the speed of light. This theory doesn't just explain why particles have mass, but also why they have different masses. Particles that interact or couple with the Higgs field more strongly are granted greater masses. Even the Higgs boson itself gets its mass from its own interaction with the Higgs field. This has been confirmed by watching how Higgs boson particles decay. One particle not granted mass by the Higgs field is the basic particle of light, the photon. This is because spontaneous symmetry breaking doesn't happen for photons as it does for its fellow force-carrying particles, the W and Z bosons. Particles like protons, made up of quarks, get most of their mass from the binding energy that holds their constituents together. While all this conforms well to theory, the next step was to discover evidence of the Higgs field by detecting its force-carrying particle. Doing this would be no simple task. In fact, it would require the largest experiment and most sophisticated machine in human history. In this way, the search for the Higgs boson itself has pushed both particle accelerator and detector technology to its limits, with the ultimate expression of this being the Large Hadron Collider. An especially important term is the Higgs boson's interaction with itself. To help pin down this and other Higgs properties, scientists are looking forward to collecting more data. Scientists turned on an upgraded LHC for a new round of work early in the year. At the time of the Higgs discovery, collisions at the LHC reached an energy of 8 trillion electron volts. These higher energies offer opportunities to spot heavier particles, and the high-luminosity LHC, a more powerful iteration of the LHC, is expected to start up in 2029. Recently, the international LHCb collaboration with the Large Hadron Collider observed 3 never-before-seen particles, a new kind of pentaquark, and the first-ever pair of tetraquarks, which includes one new type of tetraquark. The findings presented at a CERN seminar add 3 new exotic members to the growing list of the new hadrons found at the LHC. These will help physicists better understand how quarks bind together into these compound particles. Quarks are elementary particles that come in 6 flavors, namely up, down, charm, strange, top, and bottom. They usually combine together in groups of 2s and 3s to form hadrons such as the protons and neutrons that make up atomic nuclei. More rarely, however, they can also combine into 4-quark and 5-quark particles, or tetraquarks and pentaquarks. These exotic hadrons were predicted by theorists at the same time as conventional hadrons, about 6 decades ago, but only relatively recently, in the past 20 years, have they been observed by LHCb and other experiments. When the LHC was first fired up in 2008, there were hopes beyond just discovering the Higgs boson, which mostly just answered the unclear question about matter that few lay people had ever bothered to wonder about. One theoretical physicist, Erez Etzion, believed it might advance our understanding of other dimensions. Others hoped it would unlock the secrets of dark matter. None of that happened, and the LHC failed to generate headlines for years. The LHC was taken offline for upgrades in 2018. Now, the LHC has finally come back to life, and CERN is taking a minor victory lap over the aforementioned discovery of a previously undiscovered type of pentaquark and 2 new tetraquarks. Most of the exotic hadrons discovered in the past 2 decades are tetraquarks or pentaquarks containing a charm quark and a charm antiquark, with the remaining 2 or 3 quarks being an up, down, or strange quark or their antiquarks. But in the past 2 years, LHCb has discovered different kinds of exotic hadrons. 2 years ago, the collaboration discovered a tetraquark made up of 2 charm quarks and 2 charm antiquarks, and 2 open charm tetraquarks consisting of a charm antiquark, an up quark, a down quark, and a strange antiquark. And last year it found the first ever instance of a double open charm tetraquark with 2 charm quarks and an up and down antiquark. Open charm means that the particle contains a charm quark without an equivalent antiquark. These findings are little steps into the discovery of what holds our planet in place. While some theoretical models describe exotic hadrons as single units of tightly bound quarks, other models describe them as pairs of standard hadrons loosely bound in a molecule-like structure. Only time and more studies of exotic hadrons will tell if these particles are one, the other, or both, and what significance they play into the search for the formation of life. Like and share the video with your friends, and don't forget to subscribe. Turn on post notifications to confirm your subscription.